So this is the answer key for exam number 2, the practice test. So the test starts off with a reaction identification section, which asks you about all these reactions here and which one is a precipitation reaction. So remember, in precipitation, we're looking for aqueous going to solid. This is our precipitate. So none of these, so this is gases, aqueous, solid. Gases going to gas, aqueous going to liquid. So B is our precipitation reaction. Number 2 asks for 2 examples of redox reaction. This one's a little tougher, but one key is always to look and see, hey, this zinc is by itself. That means it has an oxidation state of 0. Here, in zinc I2, it's not going to be 0. Instead, it's going to be positive 2. Here, number B, it would be tougher to find. If I look at C, well, here's O2. That's 0. Here in CO2, that oxygen is negative 2. So that means A and C are redox reactions. Which one's a decomposition reaction? Remember this, we're looking for one reactant going to more than one product. And the only one that fits that is A. And number 4 asks for a combustion reaction, which is reacting with O2 to form CO2 and water. So that is C. Now on to some quick questions. So use the balanced chemical equations to answer the following questions. How much H2 are needed to react with 1 mole O2? So 1 mole O2, 1 for 2. And this is the one, if you could do this without writing it down, that's fine. So it's 2 moles H2 if you don't need to do the work. Now if we need 3.5 moles of H2O, and we want to know how much HCl forms, well, it's 1 to 2, so 3.5 would be 7 mole HCl. Moving on to number 6, we're told we have 50 grams of one compound, 100 of another compound. They react. After reaction, how much of the limiting reactant remains? Oh man, is it compound A or compound B? Well, it doesn't matter because it's limiting reactant. And we know that the limiting reactant gets all used up. So none of it remains. So now, part B, we're asked, a lab experiment produces 32 grams of product, but 58 grams were expected. What's the percent yield? So percent yield is actual over theoretical times 100%. This is my actual yield. Expected, that's what my theoretical yield is. So I can plug in 32 over 58 times 100%. I get a percent yield of 55%. Number 7, in dilution, does the molarity increase, decrease, or stay the same? Well, dilution is decreasing. Do the moles of solute increase, decrease, or stay the same? Well, if we're talking about the moles of solute, the one thing in dilution is that must always stay the same. If I add more, it's not truly dilution. All right, number 8, what solids form? When we have sodium bromide and NH4PO4. This is ammonium phosphate. So we have Na+, Br-. We have NH4+, ammonium, and PO4. This is 3-. This should actually be 3. So in this case, we look at this and we say these could form or these could form. Well, looking at so we have NH4Br or Na3PO4. Well, looking back at our solubility rules, cations, Na+ is always soluble, ammonium always soluble. So that means These two are all soluble, so we have no precipitate. Moving on to 8b, we have rubidium chloride, so that produces Rb plus, Cl minus. We have lead, this is 2 plus and NO3 minus. We can get this or we could get this. So we could form rubidium nitrate or lead 2 chloride. Looking at these two, rubidium, always soluble. Chloride is soluble except with lead. So that means lead chloride, that is insoluble. So PbCl2 is the precipitate that forms. Moving on to number 9. Are the following solutions neutral, acidic, or basic? So in this we're looking, do we have more OH minus or H plus? Well, 1.2 molar HCl will give us 1.2 molar H plus. Then we'll get 2.4 molar OH minus. So we have more OH minus, so that means it's basic. Looking at question number 2, it's very similar except my acid here. It's H2SO4. So if I have 1.2 molar, I'm actually going to get 2.4 molar H plus. So this is going to be neutral. Okay, identifying oxidation numbers, number 10. So in these, we're always looking at what rules we know. So we know oxygen's -2, hydrogen's +1. We have 1 oxygens, that means still -2 here. This is +2. So now +2 and -2, so that means the carbon has to be 0. And so that top row, those are my oxidation states. For calcium chloride, we need chloride is -1. We have 2 of those, so that means the calcium has to be +2. We could also just look at the periodic table and say, hey, calcium usually makes +2 ions, chlorine makes -1 ion. Write out a balanced chemical equation with states for the combustion of C4H6. So C4H6 reacts with oxygen to form CO2 and water. This is the basic combustion. Okay? And so now we have to balance it. So there need to be 4 C's. I need to have, so there were 4 carbons. Now there are 6 hydrogens, 2 oxygens, and here I have 8 plus 3, I have 11. So I could put something in front of this O2 to balance it. If I put a 5, now I'm going to have 10 oxygens. Well, that's not good enough. So maybe I want to put a 6. This would mean now I'd have 12 oxygens. So 5's not enough, 6 is too much. So instead, I'm going to put on there 5/2, or 11/2. And now I have a balanced equation, but I don't like it because I have this half here. So I multiply everything by 2. And now I can add in those states. I'm told it's gaseous C4H6. O2 is gaseous. CO2 is gaseous. And water is gaseous. And then why are the products in the gas phase? Well, we burn things in order to get heat. There's a lot of heat coming out of there, a lot of energy that turns those, that makes sure those are released as gases. Question number 12. Write the net ionic equation, including states for calcium chloride plus ammonia, or silver nitrate going to calcium nitrate plus silver chloride. So a net ionic, that means we need to turn these into ions. So I can say, all right, I have calcium 2 plus Cl minus plus 2 silvers plus 2 nitrates. Here I get calcium 2 plus and I get 2 nitrates. And my silver chloride, that one I don't break apart. And I don't break it apart because it is insoluble. So everything else is aqueous, silver chloride is solid. This is my complete ionic. I want net ionic, so now I need to see what is on both sides. And from this I get Cl minus plus 2 Ag plus going to 2 AgCl. I need to make sure I put in all the states, and I am done. Okay, moving on to some calculation problems. So we're asked to calculate the mass of H2SO4 in 2 liters of 18.5 molar H2SO4. So 18.5 molar means 18.5 moles per liter. So if I multiply this by 2 liters, I'm going to get 37.0 moles H2SO4. But I want mass. I want grams. So I need to take this 37.0 moles and I need to find some way to turn that into grams. Well, moles to grams, that's molar mass. And so I look at the periodic table and I can find, okay, it's 98.078 grams for 1 mole. This is 2 times H plus S plus 4 times oxygen. And this gives me 3,630 grams H2SO4. And these have 3 sig figs, so my answer has 3 sig figs. Number 14. So, what volume of a 2.5 molar NaCl solution is needed to make 100 ml of 0.2 molar? So this is a dilution problem. Why? Because we have something that's concentrated and we want to make something that's dilute. And we do that by adding in water. So here is my C1, my C2, my V2. So I am asked for the V1. C1 V1 equals C2 V2. Rearranging this, V1 equals C2 V2 over C1. I can plug in 0.2 molar times 100 ml over 2.5 molar, and I get from that 8.0 ml. Or in reality, it should just be 8 ml, just because this right here only had 1 sig fig. All right, question number 15. How many grams of silicon dioxide are required to produce 355 grams of silicon monocarbide? So we have our balanced chemical equation. We can check. We have 3 carbons, 1 silicon, 2 oxygens, 2 oxygens. Great. So we want to know grams of this, but we're given grams of our product. Well, we can't go there in one step. What we have to do is we need to convert to moles. So we take this, use its molar mass to find moles of SiC, then use our balanced chemical equation to say 1 mole SiC equals 1 mole SiO2, and then use the molar mass of SiO2 which is 60.084 grams. And from that, I get 532 grams of SiO2. Question number 16. This is a titration problem. And the key to titration problems are moles acid equals moles OH minus, or molarity of my H plus times the volume of the H plus. Let me just change this up to how I presented it in class. The concentration H plus times the volume H plus equals the concentration OH minus times the volume OH minus. So I'm asked for the molarity of the HBr, so that's this, so I can rearrange it to say that is OH minus times the volume OH minus over the volume H plus. The concentration OH minus is 2.2 molar. I have 15.2 ml. I divide by 40 ml. Seeing that these are both in milliliters, they cancel out, and I get as an answer 0.84 molar. Question 17. Now this is a recall from test 1, looking at metric conversions. And hopefully this is something by now that we've figured out. We want to go from milliliters to liters. A milliliter is very small, so 1,000 milliliters in 1 liter. So we get 3.779 liters. Going from kilogram to milligram, well, we can't do this in one step because we don't have that conversion. But we can say 1 kilogram is 1,000 grams, and then 1 gram is 1,000 milligrams. Grams cancel out, kilograms cancel out, and I get 5,900 milligrams as my answer. Great. Now let's go on to some longer questions. I'll leave that there if you need it. So we have a problem where we have 15 grams of Li, 15 grams of N2. They react according to this. So we're first asked, what is the limiting reactant? So we go through the steps, and my first step is always to balance it. Let's look. We have 6 Li, 6 Li. We have 2 nitrogen, so it's balanced. Step 2. Find moles. So I have 15 grams Li. Li has 6.941 grams for 1 mole. So that is 2.161 mole Li. I do the same thing for my N2, except I have to be a little bit careful because N2 is 28.014 grams, not just nitrogen by itself. I do the same thing. I get 0.5354 moles N2. But I can't figure out the limiting reactant yet. What I need to do is step 3, and that's figure out how much LiN2 or Li3N could form. So, according to my stoichiometry, 6 moles Li is 2 moles Li3N. So that will give me 0.72 mole Li3N. Taking my N2, for every 1 mole N2, I get 2 moles Li3N. So that will give me 1.07 mole Li3N. I compare these two numbers. This number is smaller, so that means my lithium is my limiting reactant. Moving on. How many grams of Li3N are formed? Well, in order to look at this, and this is usually step 4 in the process we've been doing in class, I look and I say, well, I use this number right here. And I say I have 0.72 moles Li3N. Li3N has a molar mass of 34.83 grams for every 1 mole. So that gives me 25.1 grams Li3N. And now we are on to asking about the reactants remaining. So one of these we know right away. We have 0 grams Li. That's because it's the limiting reactant. Oops. But to figure out the N2, it's a little more complicated. We need to realize that all of our lithium reacts. So that means that we have 2.161 mole lithium reacting. And for every 6 moles lithium, I get 1 mole N2 reacting. From my balanced equation, this ends up being 0.36 mole N2 reacting. I started out with 0.5354 mole. I take the difference between these two. That gives me 0.1754 mole N2 at the end. I use its molar mass. And I get 4.91 because I started off with 3 sig figs, so I better have 3 sig figs, grams N2 remaining. And I could do a quick check and I could say, well, if I add all these up, 25.1 plus 0 plus 4.9, that gives me 30 grams. I started off with 15 grams and 15 grams, so I had 30 grams to begin with. So 30 grams goes to 30 grams. Great. Another long question. This is combustion analysis. And in combustion analysis, we're looking for an unknown hydrocarbon, its empirical and then molecular formula. So something like CXHY. So we have to take these masses of CO2 and H2O and we convert into moles of carbon and hydrogen. So CO2 has a molar mass of 44.09 and 1 mole CO2 has 1 mole C. So that gives me 0.0523 mole carbon. H2O has molar mass of 18.015, but 1 mole H2O has 2 moles H. So this ends up being 0.2087 mole hydrogen. So I have C 0.0523, H 0.2087. Divide by the smaller of them. I get CH4. This is methane. This is natural gas. This is what comes out of your stove. So part B, now we're told the molecular mass. So now from that, we can find the molecular formula. In order to do that, we need to figure out, hey, this CH4, it has n number of subunits. And so we can take the molecular mass divided by the empirical mass, 32.08. I look here, I have carbon, which is 12.011. I have hydrogen, which would be 1.008 times 4. This will give me 16.043. This gives me 2 for my N, so my molecular formula is C2H8. So let's move on. Now we're talking about a redox reaction. So we're given a redox reaction. We're asked for chromium. What its oxidation number is here as a reactant and as a product. Well, for Cr3+, it's easy. It's +3. For chromate here, it's a little bit harder. Each oxygen's -2. We have 4 of those. So that gives us -8. Whatever the chromium sum is, plus -8 has to equal -2. So that's +6. So each chromium is +6. So we're going from +6 to +3. So that means I need to gain electrons. That is reduction. Moving on to iodine, we have, this is much easier, we have I-, so that's -1. We have I2, it's by itself, so that's 0. I- to 0 means you lose an electron, and that is oxidation. This makes sense. Something has to be reduced, something has to be oxidized. And the oxidizing agent. For that, we look at whatever is being reduced. In that case, it's chromium. So we look and it's the entire compound, including the chromium. Question number 21. Balancing. So this is just about balancing. An unbalanced chemical equation breaks which law? This is the law of conservation of mass. In this reaction, what are the reactants? We have lithium and we have water. Notice I don't put the 2, I don't put the 2, it's just lithium and water. Is this balanced? I have 2 lithiums, I have 2 oxygens, I have 4 hydrogens, I have 4 hydrogens, so yes. What does this delta mean up here? Well, that means heat is needed for the reaction to occur. You need to put it on a hot plate or something else. 23 asks us to balance some chemical equations. So we have C2H4 plus O2 going to CO2 and H2O. This is a combustion reaction. So we can go ahead, we have 2 carbons here, only 1 here, so I'm going to make this 2. I have 4 hydrogens on the left, 2 on the right, so I'm going to make this a 2 here, which means I have 4 hydrogens. Now I have 2 oxygens, I have 4 plus 2, so I have 6 oxygens here, so I put a 3, that makes that balanced. 23b, KMnO4 going to K2O plus MnO plus O2. So I'm not going to start with the O. Should I start with the manganese or the K? Well, manganese is balanced, so let's start with the K. I do that to balance the potassium. Now, my manganese is not balanced, so I can put a 2 in front of the MnO. That balances that. I have 8 oxygens here. I have 2, 4. I have 1 plus 2 plus 2, so that gives me 5. So I need to put something in front of that O2. Well, just like earlier, if I make this a 2, this would be 7. If instead I make it a 3, this would be 9. Well, between 2 and 3, I'm going to put 2 halves or 5 over 2. This is balanced, but it's not that great, so I can make this 4 KMnO4 goes to 2 K2O. Oops, sorry. There we are. 2 K2O plus 4 MnO plus 5 O2. Just multiplying by everything by 2. Okay, and now our final problem. We are asked in word form that when heated, solid magnesium metal reacts with diatomic bromine gas to form solid magnesium bromide. So, this is our product. These are our reactants. So our reactants are magnesium, Mg. It's a solid. If it's a metal, it's just by itself. We have diatomic bromine gas, so that's Br2. The diatomic means there are 2 of them. And they form solid magnesium bromide. Well, if we look at our periodic table, we can see that, sorry, this is sideways, magnesium's in here, so this is 2 plus. Bromine is here, so it's 1 minus. So going back to our magnesium bromide, if magnesium's 2 plus, bromine's 1 minus, that means we have MgBr2. This is a solid. Nope, it's already balanced. 1 magnesium, 1 magnesium, 2 bromines, 2 bromines. So the last thing we have to do is say, hey, it's heated, so I'm going to put this. So this is our balanced equation.